Hello students, in today's lecture we will try to understand plasma as a fluid. We will try to see how plasma can be treated as a fluid and how this treatment is different from treating the plasma as a collection of particles and trying to understand how these particles will behave in different types of fields, electromagnetic fields. Right. So far in our discussions, it has been very simple as we have considered individual particles and we have imposed or uh, we have considered various electric and magnetic fields, let us say time dependent or time independent electric fields and magnetic fields. So, most of this discussion was under the assumption that we prescribe certain type of electric field or magnetic field and then we study what happens to plasma. Now, the entire plasma is summed up into a single particle. That is what the single particle theory is all about. So, we were only focused about how a single particle, let it be an electron or ion, will behave in the presence of these fields. Now, most importantly, in plasma or in general situations, the electromagnetic fields are not prescribed. What do you mean by prescribed? You are imposing, you are constructing a magnetic field or electric field, and then depending on this construct, you are trying to understand how the particle will move. So, this is what is called as the prescribed way of doing things, right. So, in this class, we will try to understand how is this different when you consider plasma as a fluid, not as a single particle, rather a collection of many particles where individual behavior of a single particle does not matter, only the collective behavior in the entirety of the plasma only matters. So, we will try to understand the macrophysical aspects of the plasma, right, by considering it as a moving fluid. So, we know very well that plasma given any volume, when kept in a volume, it will not occupy the entire space. Like if you put a gas in a chamber, it will occupy the space. So, unlike that, plasma has a different characteristics, right. So, when you say it is a fluid, so we have to understand the electromagnetic fields in plasma are not prescribed, rather they are determined. What do you mean by that? They are determined in the sense plasma is a collection of electrons and ions, right. So, when these particles move or gyrate, they will generate currents and they will generate electric field or magnetic field. Now, these fields that are generated by the movement of plasma will at the same time will also guide the movement of plasma. So, the plasma has to move in such a way that the electric and magnetic fields created should be consistent or should allow the plasma to move as it was moving. Okay. So, try to understand this very carefully. Okay. So, that means that this problem of understanding plasma being a gas with charged particles needs to be self-consistent in two different ways. Okay. What are the two different ways? Let us say the first one is the particles, the charged particles. The charged particles generate electric field and magnetic field as they orbit, right. We are trying to build a self-consistent picture for plasma and we are moving away from the prescribed electromagnetic fields and we are trying to understand how the electromagnetic fields are determined in a self-consistent way. Okay. So, first one is the charged particles, of course, they generate electric and magnetic fields as they orbit. Why do they orbit? As they experience an electric field or magnet, they will orbit according to the field's condition, right. Now, the field will cause the particles, the resulting field, the electromagnetic field will cause the particles to move in these orbits. Or we can go ahead and say that the resulting field of this charged particle movement should continue or should allow the particles to move in the same way as they were moving. Okay. So, this behavior has to be self-consistent. That means one has to be, we have to have this reinforcement of these two conditions going hand in hand. Only then we can expect plasma to be a stable entity, right. And most importantly, all of this positive feedback or reinforcement should happen in a time varying fashion. That's most important. So, with time varying fashion, this is the most important thing or the most difficult thing, right. Now, let us say if you are trying to understand plasma as a fluid, what will you do when you are deviating away from understanding plasma as a particle? What will you do? Let us say, for example, we will start with a single particle. Okay. Now, the particle is of course kept in an electric field or in a magnetic field. So, the particle will gyrate something like this. As it gyrates, it will generate a magnetic field, right. So, let us say we call this as the secondary magnetic field, for example. So, this magnetic field should now allow the particle to move or should allow the particle to continue moving as it was moving earlier, right. So, this is the complicacy that I am talking about. So, what I can do is, if I consider a single particle, since I know what will be the electric field that can be generated out of this particle's movement, given the velocity and the kinetic energy and etc., I can also make a measure of the magnetic field that will generate, and with respect to these two, I can be able to predict how this particle will move in a time varying fashion. So, what will be the position of the particle or the radius of the particle or any associated physical parameters that will be generated as a function of time for this particle, if it is one particle, right. Now, as it is, let us say, as it can become complicated, we can have many particles. So, approximately we can consider a typical of 10 to the power of 12 particles or electrons per unit volume. Then you can imagine how complicated this entire situation can become actually, right. So, that means that this is going to be highly computationally intensive and highly demanding, but at the end it will almost be an impossible task, because each particle's current or the magnetic field that is generated will be superimposed on the other particle, and the direction of velocity of all these particles put together will almost make it an impossible thing to achieve, right. So, now that we are trying to deviate away from the particle theory of plasma, we are able to realize that if we have to build a self-consistent picture for understanding plasma, particle theory may not be an appropriate candidate, right. So, what do? What we do is we can move away and say that generally a more acceptable theory to understand plasma behavior could be based on treating the plasma as a fluid. So, what has been found is, surprisingly, nearly 80% of the plasma phenomena observed in real experiments can be explained by a simple and crude model which is called as the fluid description of plasma. This is the fluid description of plasma. The basic difference that we have to understand is, we no longer deal with individual particles, individual electrons and ions. What we rather do is, we will look at the overall behavior or macroscopic behavior of the plasma, considering it as a single entity. Okay. So, this is just like fluid mechanics, where the identity of individual particle is neglected and only the motion of fluid element is taken into account. Okay. So, in plasma, the motion of these charges make everything complicated actually, that is the basic reason. So, fluid model can be a very good candidate. Up to 80% of the plasma behavior can easily be understood, and if you fail that, then the kinetic theory of plasma is a more involved or mathematically robust theory to understand plasma behavior. Even if that fails, then we have to go back and get to the task of tediously understanding individual trajectories of the particles, which can be like I said, very complicated and at the same time computationally almost impossible. But people have been able to do it, not to very large densities of plasma, it may be up to 10 to the power of 3 or 10 to the power of 4. Up to that, people have been able to do it. So, this is the basic understanding of plasma as a fluid, or what is the reason that you have to discuss plasma behavior using a fluid model, right. So, when you are now, you are no longer bothered with individual particles, nor that you are bothered with the electrodynamical effects, but what you are trying to see is the entire plasma as a fluid. So, it is obvious that you have to equip yourself with the fundamental laws of fluid dynamics, how things are dealt with in fluid. So, as long as it is a rigid body, we know that the body or the object has a mass, and you write your equations on that object's mass, involving the mass. So, you will think that all the forces will be acting towards the center of mass of this object. But now, since it is a fluid, you cannot pinpoint and say that this is where the fluid is concentrated. The fluid is everywhere within that enclosure, whatever. The fluid is a dispersed entity or a diffused entity, right. So, in that case, what we do is we do not pinpoint and say this is the fluid, rather we will say that we will consider a volume of the fluid and say that we will apply our laws of physics onto this volume, and we will try to understand the behavior, the physical characteristics of this particular volume, what happens within the volume, right. And we can say that the fundamental fluid dynamics is basically nothing but conserving the mass, the conservation of mass, the conservation of energy, third, conservation of momentum. So, in fluid we always apply conservation over a very small parcel of fluid, and we take the budget of physical parameters or physical quantities over this volume, right. So, what is this volume called as? So, this is an element of fluid actually. This is a parcel or this is a packet of fluid, and this element or the volume is called as the control volume. This control volume can be of two different types or two different kinds. One, a Eulerian control volume, another Lagrangian control volume. Okay. So, what happens, what is the difference between these two control volumes is that in the Eulerian reference or control volume, it is actually fixed to the coordinate axis. It is basically a parallel pipe with sides delta x, delta y and delta z. So, it is fixed with respect to the coordinate system, it is not going anywhere. So, this is delta x, this is y z. Okay. Mass, momentum and energy budgets will depend on the fluxes caused by the flow of the fluid through the boundary of the control volume. Why do I speak of budget? Budget is nothing but conservation, how much is coming in and how much is going out. If these two things are same, it will be conserved. Otherwise, we have to look for what is causing this difference of incoming versus outgoing, as simple as that, right. Now, coming back, when we consider a Eulerian control volume, the basic idea is that it is fixed with respect to the coordinate system, it is not going anywhere, but the budget of physical parameters, physical quantities is calculated by understanding how much is getting into this volume and how much is going out of this volume. That is the basic idea, right. So, in the Lagrangian control volume, on the contrary, what you do is the idea of this control volume itself is an infinitesimally small mass of particles, let us say delta m. You consider this delta m mass to be the control volume, and what you do is you see where this mass is going, how this mass is behaving with respect to time, and how the velocity of the object of this mass, everything related to this, right. So, the basic difference is the Eulerian control volume is fixed with respect to the coordinate system, and you expect the entire fluid to kind of go through it, and you calculate the budget. And in the Lagrangian control volume, you identify a small mass of particles and you name it as delta m, and you say that this mass is going from one point to another point. Okay, so this is the basic idea, right. Now, what we are trying to understand is we are trying to equip ourselves with the basic laws of fluid dynamics, because just like particle theory of plasma, in particle theory of plasma we had only one equation, which is the Lorentz force equation, and this equation was able to tell us what will be the position of the particle as a function of time under the effect of these different electric and magnetic fields. But in fluid dynamics, we have to see how this fluid as a whole behaves, this electrified fluid behaves as a function of time. That is the basic difference. So, in fluid dynamics, what we do is we use a derivative called as material derivative, also called as the total derivative, can also be called as the substantial derivative. Substantial derivative. What is it? So, when you are trying to understand the movement of this control volume or movement of fluid through this control volume, both the things, Eulerian and Lagrangian, we have to understand if it is the measurement of physical parameters inside this small volume that you are actually trying to accomplish, then it can change. Let us say if you are trying to measure the temperature inside this, the measurement of temperature inside this can change because of two things. One, let us say the fluid is passing through the volume. With time, the temperature of fluid that is getting in may differ, and as a result, you may see a variation of temperature inside this volume, right. The second type of variation that can be brought into this is that, let us say the control volume itself is moving. Now, as it is moving to a colder place, what happens? It will start telling you a different value of temperature, right. So, that means in order to account for both these variations, variation with respect to the changes in the position as well as variations with respect to time. So these two things have to be separated. Variation with respect to time, that means the fluid volume is there itself, but with time the fluid that goes through it is changing. So, as a result, the physical parameter changes, or if the control volume is being displaced from one place to another place. So, the position, the variation is now with respect to the position of this control volume, right. So, in order to accomplish a comprehensive picture of the variability of physical quantities inside the control volume, we define this material derivative or total derivative. So, this will include the variations with respect to space as well as with respect to time. Let us see how we do it. Okay. So, this is basically a Lagrangian control volume d by dt. This is called as the total derivative, capital D by dt. So, in order to derive this expression or this relation, let us say we define a variable called as temperature. T is temperature inside the control volume. So, when the fluid parcel or the control volume is flowing following the position of the fluid as a function of time. So, we can write the position x is a function of time because it is changing, y is a function of time, z is also a function of time. Now, the temperature that you are trying to measure inside the volume, let us say we draw it also for the sake of better understanding. Obviously, this is the temperature inside, right. Like I said, this temperature can change because of two different things. It can change due to the control volume being kept at different physical coordinates and the control volume experiencing different temperatures as a function of time, right. So, now the temperature can be a function of position x, y, z as well as time. So, basically we are trying to account the change in temperature as we follow the motion of the fluid along the fluid's movement, along the direction of the fluid's movement. Okay. So, if the parcel moves an incremental distance from x, y, z, t to, let us say, by a distance, incremental distance of delta x, delta y, delta z, and this incremental displacement in position happens over an incremental time delta t. Okay. So, the temperature change that can be observed within this control volume delta capital T could be the partial change of temperature with respect to x, dou by dou T of dou x into delta x, and partial change of temperature with respect to y into delta y, plus partial change of temperature with respect to z into delta z, plus the partial change of temperature with respect to time itself, right. Let us say we divide this whole quantity with respect to time, delta t by delta t. Whatever, if the parcel is moving from one place to another place, it is happening over a period of time. So, obviously, when you include only time, the variations with respect to space are implicitly covered when you say the main variable is time. You understand? If the parcel is going from, let us say, like this, it is right here, sorry. If the volume is here, so as long as the volume is here, the fluid is coming and going like this, let us say, for example. So, at t is equals to 0 and t is equals to 10, what happens? Different fluid of different temperature comes and goes. So, obviously, there will be a change in delta, there will be a change in temperature, delta T will be not equal to 0. Or you take the same time interval t is equals to 0 to t is equals to 10, and you expect that this parcel by some buoyancy is rising across this landscape, and at t is equals to 10, there is no movement in the fluid. We can make it simple. We say that the fluid is at rest. It is what? It is static, okay, stratified. But at t is equals to 10, the parcel is now experiencing a different air or different fluid around it. So, obviously, there can be some delta t which will not be equal to 0. So, what this total derivative does is that it accounts for changes which happen with respect to position as well as with respect to time. But ultimately, both these things, both these scenarios have to happen over a period of time. So, it is obvious that we take a derivative or we divide this with respect to time, then we will capture both the different types of variations in a single equation. So, what will happen? The equation will simply look like this: dou t by dou x delta x by delta t plus dou t by dou y delta y by delta t plus dou t by dou z delta z by delta t plus dou t by dou t or delta t, right. So, delta x by delta t, the rate at which position changes with respect to time along x direction, is nothing but the velocity along x direction, which is called as u. You can call it as u, or before that we can get rid of this delta t by imposing that limit delta T tends to 0, we can write delta capital T by delta small t as, okay. Using the limit, we can write d capital T by d small t is dou T by dou T temperature plus dou T by dou x into dx by dt plus dou T by dou y dy by dt plus dou T by dou z dz by dt, or dt is plus right. So, we have this. So, dx by dt is u, v, w are the velocity components along the 3 directions. Right? We can simplify it by using the gradient and say that dou T by dou T will remain as it is plus u dot del T. So, this can be written using the gradient like this. What you see here is, this is the total change in temperature which happened over a period of time. Okay. That is equal to the rate of change of temperature which happened only because of time. That is one situation which can exist all by itself also. It is not necessary that the position or change with respect to position should always be there. But another thing is the advection. This term is called as the advection. So, this refers to change in the properties, change in the physical quantities at a fixed location due to replacement of original air or original fluid with a new fluid. Okay. You understand? So, the advection, the fluid volume is not going anywhere, rather the fluid volume as it as new fluid or the fluid that is there inside is replaced, the change in the physical quantity is given by this advection term, right. So, this one, the first term is called as the total derivative, total change. Okay. This one is the local change, and the third parameter is called as the advection, right. So, now we have understood what is the importance or the necessity of the fluid theory of plasma, and what are the complexities if you continue using the particle theory of plasma. And then, in order to proceed further into the understanding of plasma as a fluid, we need to equip ourselves with the fundamental laws of fluid dynamics, and the total derivative or the understanding of total derivative is very important to understand plasma as a fluid. Okay. We will continue this in the next lecture.